In this video, we'll look at a proof of how the master theorem works. So a reminder, the master theorem states that if t of n equals a of t of the ceiling of n over b plus a polynomial, then we have these three cases. So let's do as we normally do with a recurrence relation. Let's create a recurrence tree. So we'll have our recurrence at the top, just to remind ourselves what that is. Let's assume, for the sake of argument, that n is a power of b. That's a reasonable assumption, since we can always just pad n to be larger, right? If we increase it by no more than b, we can get to the next closest power of b. And then this will be a simpler analysis. So we have our problem n. At the next level, we break the problem down into a copies of a problem n over b large. So level 0, we have a problem of size n. Level 1, we have problems of size n over b. At the general level I, we have problems of size n over b to the I. And at the bottom level, which is level log base b of n, we have problems of size 1. All right, how many problems are there? At level 0, there's, of course, one problem. At level 1, a problems. And in general, at the ith level, a to the I problems. At the log base b of n level, it's a to the log base b of n. How much work do we have to do? Well, work is just a function of how many problems we have and the amount of work for each problem. So at level 0, we have just big O of n to the d work. There's one problem, and it takes big O of n to the d time. At level 1, we have a problems, and each of them take big O of n over b to the d work. Okay, we can pull out the a and the b and the d to be all together, and that's just big O of n to the d times a over b to the d. At the ith level, we have a to the I problems, and each one is big O of n over b to the I to the d. Okay. Again, we can pull out the a to the I, the b to the I, and we're left with big O of n to the d times a over b to the d to the I. And finally, at the bottom level, it's just a to the log base b of n, because the problems are all size 1, which is just big O of n to the log base b of a. Okay. So the total amount of work is the summation from 0 to the log base b of n, big O of n to the d, times the quantity a over b to the d, all that to the I. So let's look at what seems like a slight digression, and that is geometric series. So a geometric series is a series of numbers that progresses by some multiplicative factor. I'll give you an example. If we take 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, that's a geometric series, okay, where our factor is a factor of 2 at each time. Just as well, we could have a geometric series that goes down. So we could have, for instance, let's say 10,000, 1,000, 100, 10, 1, where we're going down by a constant factor of 10 at each point. Now it turns out our multiplicative factor, let's call that r, as long as r is not equal to 1, we have a simple closed form for this. This is just a times the 1 minus r to the n over 1 minus r. And it turns out that in big O notation, what happens is we care about the largest term, okay? So our sum is going to be bounded by a constant times our largest term. So if r is less than 1, then our largest term is the first element, a, and therefore our solution is big O of a, okay? Because that's our largest term, it gets smaller, 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 smaller. And as long as it's by this multiplicative factor, then all that really matters is this first term, because the rest of it sums to no more than a constant times that first term. If, on the other hand, r is greater than 1, then what matters is the very last term, because that's the biggest term, and all the previous ones are smaller and smaller. So it's smallest, larger, 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 largest. Okay? And so that largest term is a r to the n minus 1. So in a geometric series, we care about either the first term or the last term, whichever one's bigger. Now, if we take that back to the case of our recurrence tree, we notice our summation here. This is the same summation we had from our recurrence tree. And we see that we have a geometric series. Okay? A is taking the place of big O of n to the d, and R is taking the place of A over b to the d. Okay, so our multiplicative factor is A over b to the d. And there are three cases. You remember as we stated the solution of the master theorem. Case one is d is greater than log base b of a. Well, it's equivalent to saying A over b to the d is less than 1. So now we have our multiplicative term is less than 1, so it's getting smaller and smaller and smaller. That means that the largest term is the first term, and that's the one that we have an order of. So this is big O of, officially big O of n to the d, which is just the same as big O of n to the d. Case 2, where d equals log base b of a, and equivalently a over b to the d is equal to 1. Well, if a over b to the d is equal to 1, remember our geometric series formula didn't hold. All right? So we're going to just have to calculate this. But if a over b to the d is 1, then a over b to the d to any power is still 1. So that means that our summation is just the summation from I equals 0 to log base b of n of big O of n to the d. And that's just 1 plus log base b of n, because that's the number of terms in our summation, times big O of n to the d. Well, the 1 is a lower order term we don't care about, and the log base b of n can just be treated as log n, because a base change is just some multiplicative factor, and that disappears in our big O notation. So we end up with, as we stated in the theorem, big O of n to the d times log n. And then our final case is d is less than log base b of a, which is equivalent to saying a over b to the d is greater than 1. So here, our multiplicative factor is greater than 1, so our smallest term is the first term, and our largest term is the last term. So in this case, this is big O of, our last term is big O of n to the d times a over b to the d log base b of n. So I is log base b of n. Well, this is a bit of a mess. Let's see whether we can fix this a little bit. So let's go ahead and apply the log base b of n power separately to a and b to the d. So we have in the numerator a to the log base b of n, and then the denominator b to the d times log base b of n. Well, b to the log base b of n is just n, so that's going to disappear down to n to the d in the denominator. In the numerator, a to the log base b of n, by logarithmic identity, is equal to n to the log base b of a. So we can swap those out or two. And now if we compare big O of n to the d and n to the d, we know big O of n to the d is bounded by some constant, k times n to the d. So we have k n to the d divided by n to the d, which is just some k. And that constant can go away because we're still talking about big O notation. So we're left just with big O of n to the log base b of a, which is what we have for the final case. So the master theorem is a shortcut. Our master theorem, again, is a restatement, is here. I have a secret to tell you, however. I do not remember the master theorem, and I don't actually even look up the master theorem. Here's what I do. When I have a recurrence of this rough form, I look at the amount of work done at the first level and at the second level, which is a very easy calculation. And then I just say to myself, is that the same amount of work? If it's the same amount of work, it's going to be the same amount of work all the way down, and so we're going to be in case 2. So it's going to be the amount of work at the first level, which we know is big O of n to the d, times log n, because there are that many levels. On the other hand, if the first term is larger than the second term, I know the first term is going to dwarf all the other terms, and so we're left with just big O of n to the d. And finally, if the first term is less than the second term, I know they're going to keep increasing, and it's the bottom term that I need. And that is just going to be the number of leaves, which is n to the log base b of a. The master theorem is really handy to use, whether you memorize it, or you have it written down and use it, or, in my case, you sort of recreate it every time you need it. Thanks.